Can everyone see my screen?
Yes.
Okay, yeah. So should I just start when I'm ready?
Yeah, you can go ahead and get started.
Okay, yeah. So yeah, hi everyone. I'm I-Hsuan Kao. I'm a third-year PhD student at the Department of Physics at Carnegie Mellon University. Today I'm going to share our exciting results on using the spin current in WTE2 to switch a perpendicular magnetized ferromagnet. Let me zoom in. So the current-induced switching of perpendicular magnetization is important for magnetic memory technology. And one way to achieve this is to use the spin orbit torque generated in heavy metals or topological insulators. But this kind of anti-damping torque in this category remains in plan due to their two-fold rotational symmetry. So when you want to use spin orbit torque in heavy metals or topological insulators to switch a perpendicular magnetization, then it will require a bias field, in-plane bias field to do deterministic switching. So here, instead of using heavy metals or topological insulators, we use WTE2, which is a transition metal dichalcogenide with low crystal symmetry. And precisely, if you look at the crystal symmetry here, you can notice that in the AC plane mirror symmetry is broken, but the BC plane, I think this is AC plane. AC plane mirror symmetry is broken and the BC plane mirror symmetry is preserved. And because of that, it has actually been shown that if you apply the currents in the A direction, then you can generate an out-of-plane anti-damping torque. If you instead apply a current in the B direction, then you could not generate an out-of-plane anti-damping torque. Although it has been shown that it can generate an out-of-plane anti-damping torque, it has no evidence that you can actually use this torque to switch perpendicular magnetization. It may not be strong enough. So to demonstrate this, we use WT2 as our spin source, and then we use iron germanium telluride, which is FGT, as our perpendicular magnetized ferromagnet. And so this is our device. We stack FGT and WT2 on a pre-written electrode, which is in a whole cross. And the reason why we make it whole cross is that so that we can apply the current in different axes. So now I quickly jump into our results. So in the STOT results, we pose the current along the axis, and then we measure the whole resistance to monitor the magnetization of FGT. And let's say, so first, if we try to apply the current along the A-axis, and then we prepare the magnetization in a positive state, and we sweep the current from 0 milliampere to 10 milliampere, and we find that the magnetization stays in positive state. But when we again set the magnetization in positive state and switch the current to negative current, we find that it jumps to the negative current state. So this means, and then we show that we can do this we can switch the magnetization depends on the current direction. And that's not the case if we do the same thing for B-axis. So this very big difference show that we can use the auto-plane anti-damping torque in WT to switch the perpendicular magnetization. Thank you. Should I stop sharing or should I just?
You can continue sharing. We've got 3 minutes for questions. So judges first, but audience members can jump in.
Erin, do you have a question, Erin?
Sure, yeah. I have a quick one. So you talked about WTE2. I was wondering if other TMDs have been tried, or if you plan on trying other TMDs, or what's the particular advantage of using WTE2?
Yeah, so I think another crystal that have very similar properties is MOTE2, and it has actually been theoretically predict that it can generate the same similar torque. So we actually have the plan of that, and we actually just ordered the crystal recently. So we are planning to make that device and try to demonstrate that this can also be done in different kind of crystal, not just in WT2.
So I'll ask a question. In this middle row, middle column, bottom
yes.
figure, you have, it looks like a train of current pulses and then the magnetic response. So yes. I'm kind of familiar with, for example, if you have a train of voltage pulses and you get a current response, that you need some reasonable dynamic range to have differentiable states. Yeah. Teach me what's happening here with this MZ value. How distinguishable do they need to be for this to be useful?
Oh, I see. You mean like how, I see. So I think for them to be useful, typically now in the actual technology, you use like tunnel junction, magnetic tunnel junction. So I think you need it to be like the difference between them in resistance might need to be like 20 or 30% or even higher. And for here, actually, I think I remember I forget what's the actual value here because I normalized to the whole resistance. But we measure it in the whole resistance. But I think
can you just tell me what MZ means? I see it says plus or minus 1, but there's no units, so I don't know what it is.
Yeah, so MZ is the perpendicular normalized magnetization. So when you measure the anomalous Hall effect, you can see that if you switch the magnetization, you can see a 2 different state. So this is the saturated state. Yeah, okay. And when one is, for example, when you apply a positive magnetic field upward, and then you set the magnetization to that state, and then that's what you observe there. If you switch the magnetic, so that's basically 2 different bistable states.
20 seconds, if anyone's got one more question.
Oh, yeah, I have another question. Hi, I-Hsuan, this is Feng here. I'm also one of the judges. So great presentation. Could you comment a bit? So it looks like the current needed is in the order of almost up to 5 to 10 milliamps. So that's fairly high for typical electronics. Could you comment how scalable that it is, or do we have to maintain that large current density?
No, so actually the current density, if you if you want to compare how much energy you need, you actually need to compare current density instead of current. Mm-hmm. And because so this is the van der Waals heterostructure, so typically the size is bigger, and this is actually micron size. So if you calculate the current density, it is just about, so I think 10 milliampere correspond to 10 to the power of 11 ampere per meter square, which is actually not so big. And if you try to make this device into like nanoscale, you can actually further decrease the current you need to switch the magnetization.
Right. So from what you mentioned, I understand is that the current density is going to be fairly constant even when you go down, or do you expect the needed current density to be slightly different when you go down to, let's say, 50 nanometers versus micron scale?
Yeah, actually, if you make the magnet smaller, you should expect that their corrosive field will be smaller too. So it will be actually easier to switch in principle. The anisotropy will be smaller. And also if you can make so our FGT here is about 4.1 nanometer. If you try to get an FGT that has like, for example, like monolayer FGT, then you can actually, that will have a smaller magnetic moment. So that means you can further decrease the current density you need to switch the magnetization. And of course, you can also use other material, which have like a smaller magnetic moment.
Great, yeah, thanks, Isha.
Very good. I'm sorry, we've got to move on to the next. Next up is Phillip. If you could start sharing your screen. You'll have 3 minutes to present and 3 for questions.
Okay. Oh, goodness. Sorry, just a second.
That's okay. It's classic Zoom.
Yeah, so apparently you can't see my screen, can you?
No.
Yeah, can we come back to me? It's saying I need to quit Zoom to allow it to get permission to share screens.
That's fine. That's fine. Maria, if you're ready, we'll come back to you, Phillip.
Yeah, sure. Okay. So you can see my screen? Yes? Okay, awesome. Okay, so hi everyone. I am from the physics department. So today I'm going to be talking about a project where I've been parametrically controlling the states of my qubit via a bath. So just to get started, we wanted to make a system in which we could control couplings between our qubit, in this case, a transmon qubit, and a bath, so that we could have full control over the environment in which our qubit lives, so that we could perform quantum simulations on it, for example. So the system that I'm going to be using is where I couple a transmon qubit and a snail. And a snail is a superconducting quantum object that is, it has these really important feature where you can tune it so that the high order Hamiltonian terms that are above third order, so terms that are using raising and lowering operators of S, say S plus S dagger, we want to use the S plus S dagger cubed term, and all of the S plus S dagger to the fourth and so on terms we can tune away. So when I hybridize this snail with a transmon qubit, and the transmon features fourth order terms, and those fourth order terms will come into play in a few minutes, I'll show you. But so when we hybridize them, we're going to get this Hamiltonian that has this HSQ that I'm showing, where when I drive a certain parametric process, so if I pump my snail, I effectively, so for this third order term, I effectively pump getting the second order term, where when I apply this gain process that I'm showing in this light blue, I'm going to get a photon each in my snail and my qubit. Whereas if I pump this conversion process, a photon in the qubit is at the expense of a photon in the snail and vice versa. And then this fourth order term that comes from hybridizing the snail and the qubit is actually not a problem. It's not going to shift my frequencies away because I'm designing my snail to be really short-lived. And this little cartoon shows what it actually, what this experiment looks like. You'll see I have my snail and my qubit on a single chip of sapphire opening up into a larger 3D coaxial cavity that's made out of aluminum. And I use this cavity for readout. Okay, okay. So moving forward, I was talking about these parametric processes that we can apply. So one of them, I want to create this kind of photon ratchet, where in my hybridized system with orange numbers representing state of the snail, green letters representing state of the qubit, I want to be able to take my qubit effectively from G to E. And I'm going to do that with this drive. So when I pump my snail at the sum of the
30 seconds.
and the qubit's frequency, I'm able to bring my qubit up to the excited state and I allow my snail to quickly decay so that I get this effective gamma GE rate. And I can do the same process for applying the conversion tone, where I bring my qubit from E to G effectively through this indirect drive through the snail. And I'm running out of time, but here's some data taken where I can effectively bring my qubit, I can balance its up rates and its down rates so that I have full control over the rate at which my qubit gets to a steady state of my choice and what that steady state is. And I can apply multiple parametric pumps simultaneously for even further control. And moving forward, we want to be able to create an array of these where I can control parametric couplings between sites. So I think that is my time.
Great, yeah, thank you, Maria.
Okay.
And we've got 3 minutes for questions. So judges priority and audience after.
I'll start with a really quick basic one. What's a transmon?
Sure, yeah, so a transmon is if I have a Josephson junction, which is like a nonlinear inductor. So it's for us, it's a sandwich of superconductor, insulator, superconductor. And it has this feature where instead of having a harmonic oscillator with, say, a perfect parabolic potential energy curve, where all of the energy levels are evenly spaced, this transmon, in having this nonlinear term, it picks up this little bit of fourth order so that the parabola gets effectively stretched so that the energy level spacings of my harmonic oscillator now are all unique spacings, so that I can pick out, say, my GE transition and say that that is uniquely my qubit basis.
I see. Okay, that was a great explanation. Thank you.
Thanks, Maria. This is Feng here. So that's a great presentation. So I'm not too familiar with this system, but could you let me know, is there any temperature limitations? Like, do you expect this to work better at below certain threshold voltage temperatures, or you expect it works pretty well?
So this all happens, we do this at the bottom of a dilution refrigerator because we want to make sure that our qubit is as protected from any kind of outside heating or excitations that are going to disturb it. And So that's why we make all of our circuits, we print them out of aluminum, which is to make all these superconducting circuits. And our cavity is aluminum. So this system is the temperature of your system, the actual temperature does limit how well you can put your qubit in the ground state, for example. So we do want this to be as cold as possible. So in reality, our fridge gets down to 20 millikelvin.
Wow, okay. Okay, so that's very interesting. Yeah, thank you, Maria.
Do we have time for one more or should we move on?
You've got 45 seconds, so if you can fit it in.
Challenge, Maria. I want to hear more about your future plans with this controlling the parametric coupling between an array.
Yeah. So
how you would do that, challenges you would expect to run into.
Yeah, so you can imagine that I could hook this system up to an array of, say, linear resonators, and I could control coupling between those resonators with one of these nonlinear systems like this. And I can use this snail, this parametric object is effectively a quantum amplifier. So I can control couplings between, say, neighboring resonators that have this nonlinear qubit in them by turning on and off different kind of parametric processes between different resonator sites in my array, for example.
Thank you.
And that is perfectly timed. Thank you,
Okay.
Maria.
Thank you.
Philip, are things going better on your end?
Yeah. Okay, is it working?
Okay, great. Yes, we can all see your screen. I'm going to go ahead and start your time. You've got 3 minutes.
Excellent. Okay, so I'm from Oak Ridge National Lab from the Quantum Computational Sciences group. So the quantum approximate optimization algorithm, or QAOA, is an approach to solving combinatorial optimization problems with the quantum computer. The goal of the problems is to find a bit string Z that maximizes a cost function C of Z. Quantum computers may soon outperform conventional computers on these problems. To solve the problems, QAOA translates the cost function into a quantum operator and the bit string into a tensor product state of coupled two-level systems called qubits. The total state psi of all the qubits evolves in time in a way that depends on the cost function operator and on p layers of variational parameters. The variational parameters are tuned with the help from a conventional computer. The idea is to prepare state psi and measure them with the quantum computer. Each measurement gives a bit string Z. The Z are sent to a conventional computer to calculate the cost function and to calculate new optimized variational parameters for the quantum computer. This continues in a loop until the average cost function converges to a maximum. The final answer is the measured state Z that maximizes the cost function. I focused on the max cut problem, which aims to separate vertices of a graph into two groups so that the maximum number of edges is shared. People have looked at QAOA with max cut on simple sets of graphs. My goal is to understand how QAOA performs across more general sets of graphs. I simulated QAOA for every connected non-isomorphic graph with 9 or fewer vertices. I analyzed QAOA performance in 2 different ways. The first way is based on the expectation value of the approximation ratio R, which tells how close an average result is to the maximum cut. The figure shows a distribution of the R for the 853 unique graphs with 7 vertices. The approximation ratios increase with the number of layers P as more variational parameters are added to tune the state. The distributions become more narrow as P increases, so the different graphs are performing more similarly to each other. Thus, the R is not very sensitive to graph structure. A different way to analyze QAOA performance is based on the probability to obtain the maximum cut. In other words, how likely you are to get the best possible outcome. Here, the distributions become more spread out as P increases, showing that different graphs have much different probabilities for the maximum cut. This is much more sensitive to graph structure. If you want to find the maximum cut, then some graphs will do much better than others. To conclude, I looked at 2 measures of performance for QAOA on different graphs. The expectation value of the approximation ratio is very similar across graphs, showing that near optimal cuts can be obtained for any graph. On the other hand, if you want the maximum cut, then some graphs will do much better than others. I also found patterns in the variational parameters, but I don't have time for these now. In the future, it will be very interesting to understand which specific graph properties are correlated with the best performance in QAOA. This will guide us in choosing applications for quantum computers where QAOA can outperform conventional algorithms.
Thank you, Philip. We're open for questions.
Great. Thank you, Philip. This is Feng here. So this is a very interesting talk. You mentioned that the probability is very sensitive to different geometries or graph structures.
Mm-hmm.
Could you use that for real applications, or do we want to improve the insensitivity to those?
So the idea that we have going forward in this is to try to find what specific graph properties have good probabilities for the maximum cut, or for whatever, you know, optimization problem you're interested in. And then if you're a company in the future, or you're trying, you know, you have an application where you're trying to use this algorithm, or you're trying to figure out how you want to solve the problem, let's say, then you could say, well, do my graphs have these properties? And if so, then that would tell you to use the quantum approximate optimization algorithm. And if they don't have properties that make it work well, then you might want to use something else. So I think that the motivation is to try and figure out when is this algorithm going to work well, and then figure out what are the applications, you know, that have those properties where we can use this quantum algorithm to do better than what we can do right now.
Right. Great. Yeah. Thanks, Philip.
Yeah.
So another question, you discussed the expectation value of the approximation ratio and then the probability to obtain the maximum cut. And from what I understand, you want to maximize both of these in choosing your problems. I was wondering if either of these factors is more important, like if you would prioritize maximizing one over the other, and why?
Yeah, good question. So, you know, it sort of depends on the application you're trying to do. I guess the maximum cut is the best possible outcome. And if at all possible, you want to get the best possible outcome, right? For your optimization problem, but it's not always possible. And so in that case, you might be happy to just have a good answer on average. And that's what this expectation value of the approximation ratio would tell you. So for really complicated problems, you know, like if you're trying to schedule a bunch of airplanes at airport or something, you might not be able to have a good probability for the true maximum. And so you'd want to maximize, you know, what's the chance of getting a good result on average. But at the same time, you don't want to totally neglect this probability for the maximum if it's possible to have a good maximum probability for the maximum. Does that answer your question?
Yeah, that helps. Thank you.
Yeah.
All right. Thank you, guys. We are at time. Thank you so much, Philip. Our next presenter is going to be Christopher Petroff. Hi, Christopher. You can go ahead and share your screen whenever you're ready. Okay, great. And you've got 3 minutes.
Great. So I'm going to talk to you briefly about my work on intrinsically polar piezoelectric self-assembled oligopeptide monolayer devices. So first off, have an introduction. Piezoelectric devices interconvert force and charge, and they can be used for things from varying from sensors to energy harvesters to actuators. Traditional piezoelectrics are hard, brittle ceramics, but we're looking to develop some newer, flexible, biocompatible ones. So a brief overview of my devices. So essentially grew self-assembled monolayers of oligopeptides on gold surfaces using a thiol linkage through the cysteine residue. And then we just applied another electrode on top, and then we compressed these molecular springs, which produce current. Then we just take the current and we integrate it and plot that against charge, and we can use that to slope of that line is get charge plot against force. The slope of that line is the piezoelectric response. So we looked at the response of a number of different variables. First off, we looked at the effect of using amide-terminated peptides versus carboxylate-terminated ones. And despite the fact that the carboxylate ones have a higher dipole moment, the amide-terminated ones are actually produce higher responses. We also looked at adding a dodecane thiol, just kind of a rigid alkane thiol, to the opposing electrode, and that surprisingly increased the response. And finally, we saw that varying the length of the peptide, so varying the length of the spring did not actually affect the response. So next, to help explain our responses, we did some electrodynamic simulations. And those showed us that the amidated peptides are more rigid than the carboxylated ones, which can help explain why we saw why the carboxylated ones were lower response. Sorry, the amidated ones were less rigid. Finally, we looked at device stability. So when stored under vacuum, things were stable for several months, as you'd expect for a monolayer. But under atmospheric conditions, things decayed very quickly. But if we made a sealed device, we could things were stable for up to 2 weeks under ambient conditions. So to review, grew these monolayers on a self-assembled surface. We compressed these molecular springs, measured the current, integrated that to get charge, plotted against that against force to get the D33 response, which we saw maximum response of 9.8 picocoulombs per Newton, which was maximized by the amide termination, adding a DDT monolayer, but was not really affected by peptide length. And the peptides were stable for 3 months under vacuum and over 2 weeks when sealed from the environment.
And that's about time. Thank you so much, Christopher. It is open to questions.
I'll go first. I really liked your summary at the end. That's super cool how those are like sketched. That's really cool. So I don't know a ton about piezoelectric materials, and you mentioned that you're surprised, or you made some comment about like this one had a bigger dipole, but it had a lower electric response, piezoelectric response. I think you said that. Yeah. Could you tell me, is there a known established relationship between dipole and piezoelectric response of materials?
Yeah, so normally traditional piezoelectrics are ceramics. And so then based on the crystal structure, you know, you compress and the bigger the change in the dipole, essentially the bigger the response. But when we're using individual molecular dipoles, instead of changing the actual dipole, we're more changing the dipole density. So the greater the dipole, the greater the response you'd expect. But the thing with monolayers is, unless you know the tilt angle and the packing density is exactly the same between everything, you know, then the dipole itself isn't the only factor. So we suspect that one, the dipoles are more rigid for the carboxylated ones, so they don't press as well, and two, the terminal group might affect the tilt angle of the SAM, which affects the response as well.
So it's fair to say then that it's this like unique geometry of these self-assembled monolayers and the thickness that makes it different than a bulk like ceramic crystal. Yeah, so it's definitely a different, well, it's the same overall effect. These specifics are very different. Yeah. Okay, neat. Thanks, Christopher.
Hi, Christopher. Great talk. So I'm interested. You mentioned at the end that it can be stable under vacuum for about 3+ months, and also when it's okay. So now I said it's stable for 2+ weeks when sealed. So then will it be more sensitive to things like elevation in temperature or humidity or any other stimulations?
Yeah, so it's definitely sensitive to humidity and probably the temperature. We never really looked at varying the temperature. But yeah, no, once it's brought out of the desiccator to get tested, the humidity will, the atmospheric moisture is what we think causes the response to decay. Because once it decays, as you put it back in the desiccator, take it out again to test it, then the response is restored back to the original value. But when we just sealed everything up so the atmospheric moisture can't get in, then it was stable for several weeks under ambient conditions.
Great. Thank you, Christopher.
Okay, and that is just about time. Thank you so much, Christopher. The next presenter is Chao. I've seen, oh, there you go.
Yeah, share screen.
Yes, yeah, go ahead. Okay, great. And floor is yours for 3 minutes.
Yeah, okay. So, okay, good afternoon. So my name is Chao Zhang. I'm a postdoc in Dopatics group in Department of Physics and Astronomy, University of Pittsburgh. So today I'm going to talk about the image of Haber-Bosch catalysis precursor, nitrogen potassium at atomic scale. So potassium, it has only one electron in the outermost shell, so the low ionization energy makes this material very reactive. It is found that active metals such as the potassium can improve the catalytic efficiency of many chemical reactions, such as the water-gas shift reaction, Haber-Bosch process, which has been used for ammonium synthesis. So one of the fundamental questions is how nitrogen interact with potassium at the atomic scale. So here we show the STM image of the potassium on the 011 surface. Because of the charge transfer effect, they form hexagonal structures. And after natural exposure, we can see 4 types of new structures. The type 1 structure shows a dark depressed site, type 2 structure shows dark dimer, and also type 3 and type 4 structure shows dark centered triangles and dark centered quadrangles. To unveil the microstructure of these 4 complexes, we perform the DFT calculations. And as you can see from the images, so then the nitrogen atom is bonded to the potassium and they form these 4 kind of structures. The simulated STM images agree well with our STM experiment. So the interaction between the potassium and the nitrogen can be understood from the charge transfer effect. You can see from the calculations, the potassium transfer part of their valence electrons to the nitrogen. So this is confirmed by the base charge analysis. The nitrogen molecule is negative charged, while the potassium is positive charged. As a result, the attractive interaction between the potassium and nitrogen leads to the direct bonding. Finally, we found that this structure is not stable, and the STM can induce desorption of nitrogen from the surface. So here, these 2 images shows type 1 and type 3 structures. After applied high bias voltage to type 1 and type 2 structures, nitrogen dissolved from the surface. And this is because of the electron in directional occupied states, and it decreases the attraction between the potassium and nitrogen, leading to the dissolution. Okay, thank you.
Great, thank you. We can open up for questions for the next 3 minutes.
Sure, I have some questions about your type 1 through 4 here.
Okay.
Is there a particular kind of site that is best or most desirable to get that you would want to try to engineer to, have them be all type 1 or have them be all type 4 or something like that?
Okay, so as you can see from the images, STM images, so all the potassium is bright, while after nitrogen exposure, so you can see here, for example, type 1 structure, it becomes darker than the surrounding atoms. And also for type structures, there are these 2 departed sites and all darker than the surrounding potassium atoms. And also for type 3 and type 4. Yeah, so in our experiment, we see these 4 types of structures. So, and we think, let's say because of natural absorption to the potassium atom.
Any more questions, follow-up questions? We've got about 1.5 minutes.
Yeah, if there's no questions from the audience, I can ask a question. So this is for, this work is for designing a better catalyst or for understanding a mechanism on an existing catalyst? I actually was a little bit sure of the motivation for the work.
Okay, so the motivation is want to understand what is because potassium has promotion effect, so we want to know the origin of the promotion effect, and also, but to know the origin of the promotion effect, we need to know what is the structure after absorption of nitrogen. So, yeah.
Okay, and so the idea then is if you know what that promotion effect is, you can like dial it up. Is that the idea? Because to favor this on this type of catalyst?
Yeah, right, yeah.
Okay, thank you.
Okay, if there are no more questions, thank you so much, Chao. Great talk. And next up, we have Dengyu.
Okay.
Okay, it's all you for 3 minutes.
Can you see my poster?
Yes.
Yeah, hi, I'm Dengyu from LabbyLab, and today I'll introduce our efforts on establishing a whole new method to create nanoscale structures at the LO-STO interface, and it is called the ultra-low voltage electron-beam lithography. So people have been putting efforts on quantum science and technology, and the ability to control quantum materials lies in the center of many different quantum topics. So the quantum material we're working on is lanthanum aluminate strontium titanate heterostructure, which has many interesting properties such as superconductivity, spin orbit coupling, metal-insulator transition, and so on. And our group has achieved a lot from the conductive AFM lithography technique, which is a unique technique, allows us to create nanoscale devices at the interface and exploring its properties. As we're taking advantages of the conductive AFM lithography, we're also facing the challenges and limitations it has. So basically, these are the writing efficiency issues. So for the conductive AFM lithography, the writing speed is in the range of 10 nanometer per second to 1 micrometer per second. At the same time, the devices naturally decay in the air with time scale of hours. So these two conditions constrain the complexity of the device we could write. Also, the writing canvas size is literally limited by the AFM scanning size, and the largest one we have is 90 by 90 micrometer square. So these limit us to explore the device from expand from one-dimensional to two-dimensional. So to overcome these limitations, here I introduced the ultra-low voltage E-beam lithography. It comes with the speed boost and size explosion of creating the nanoscale devices at the LO-STO interface. The writing speed can be up to 10 millimeter per second, which is 10,000 times the scale of the speed in conductive AFM lithography. And the device size can be inches as a wafer scale. So the data here shows the conductance jump we got from writing a nanowire connecting two interface electrodes at the LO-STO sample. And the acceleration voltage here is 100 volt, which is ultra low compared with normal EBL, and this is to avoid damage to the oxide structures. The process is also reversible, which means we can erase the device we wrote by a negatively biased AFM tip. And to get to know the writing resolution, we varying the gap size in the middle of a nanowire and monitoring the conductance. At the time, there is a gap with the gap size smaller and smaller. The gap will be covered by the resolution, and it gives us a resolution to sub 10 nanometers, which is similar to the conductive AFM lithography. The device shows a superconducting behavior as LO-STO to the electron gas behavior. And moreover, it can write through the graphene on top of LO-STO and creating conducting devices at the interface. The ability to write through thin layer graphene or other 2D layers will enable the dynamic gating of van der Waals materials and other 2D electron gas systems using this method defined on the layer. So we're very excited with this new technique and looking forward to other devices and experiments we can explore with this. Thank you.
Thank you, Dengyu. We've got 3 minutes for questions.
I should start my video.
Yeah, thanks, Dengyu. Very interesting talk. So I'm curious. So you mentioned there are a number of advantages of doing EBL with ultra low voltage, right? And such as minimize damage. But then what is any potential downside? What's the trade-off? We are kind of a trade-off.
That's a very good question. And actually that's why for conventional EBL, people are seeking high voltages to get better resolution and some kind of like other benefits. But we need to like avoid damage here. At the same time, when it goes to very low voltage, the electron beam is not as like high voltage, it's that straight. And during focusing, you are facing a lot of difficulties. And we need to go to a very small working distance to compensate the like low, the less electrons we can collect from the signal. So we goes to like 2 millimeters working distance, which is relatively dangerous. But it's still doable, and for LUS2 it works really well. So
yeah, thanks. That's very helpful to know. Thank you, Dengyu.
Oh, very cool work. If I could sneak one in here. I listened very carefully when you said that you used the terms that the devices naturally decay in air. What does that mean? What's decaying on the time scale of hours?
That's a very good question. Basically, for the conductive FM lithography, the mechanism we're thinking is there's a water monolayer on top of LUS2, and the positively biased tip protonized the layer, leaves the proton acting as a local top gate. And these kind of protons will like combine with the like water molecules in the atmosphere. At the same time, the electron like distributes like.
And I'm dying to ask this next question though, probably gonna go over on time. Is the mechanism then different for EBL? Because you're doing this in a vacuum now.
That was a very great question, because I don't know. Actually, the answer is we don't know the real mechanism for EBL now.
Like,
we need some like scientists to help us, but we think it has similar mechanism because we see observe similar like decaying process, and higher dose can give higher conductance jump. These kind of behaviors tells us they're like possibly similar. So
really interesting. I could ask you questions all day. I'm sure we're out of time.
Thank you. Yeah, actually, we have archived paper has the same topic. So title.
Okay. Thank you.
Thank you.
Thank you, Dengyu. Okay, and I think up next, Reedy.
Yeah. Sorry, can everybody see my screen?
There it is. Yes, it's up. All right, it's all you for 3 minutes.
Okay, so I'm Reeti, and I'm a second-year grad student at the chemistry department at UPitt. And today I'll be talking a bit about our group's work with copper selenide nanoparticles and its plasmonic properties. So localized surface plasmon resonance is actually the collective oscillation of free carriers on interaction with incident light. And it is actually an interesting phenomenon which is very unique to the nanoscale. So while this is traditionally observed only in noble metals such as gold and silver, our group has studied copper selenide as being an alternative to these precious metals. And we are interested in basically tuning and understanding its properties, the fundamental properties, such as the energy and frequency of LSPR, and also the intensity of it. So in this work, we actually aim to control the fundamental LSPR properties of copper selenide by controlling the nanoparticle size. And so to achieve this, the first barrier that we had was synthetic. So we actually developed a really straightforward benchtop synthesis of copper selenide nanoparticles in water at room temperature by just changing the amount of capping ligand that we were adding to the solution. Then the second step was to probe the LSPR properties of these copper selenide nanoparticles nanoparticles. And this peak at the NIR region is what we assign to the as the LSPR's optical feature. And if we look at the extinction spectra, the extinction spectra peak for the 3 different sizes of the nanoparticles actually lie on top of one another for a particular stoichiometry of copper selenide, and which basically tells us that the LSPR energy is independent of the nanoparticle diameter and only depends on the stoichiometry that we have. However, in order to study the LSPR intensity, we would need to look at the molar extinction coefficients of these particles. And this feature or this figure of merit is actually not straightforward to extract, and we need to use a combination of analytical tools such as TEM, PXRD, and so on. So for the interest of time, I'm not going to go into the details of it, but essentially we used Beer-Lambert's law to extract the molar extinction coefficients, and that is how we compared their LSPR intensities as a function of size. So the molar extinction coefficients that we actually extracted, we saw that they scale with the nanoparticle volume. And this made us really excited because this is consistent with the mean theory approximation that has been well studied for its noble metal counterparts.
30 seconds.
So to summarize, basically, we have studied a straightforward synthesis method, and we now know that our alternative plasmonic material actually behaves very similarly to the noble metal counterparts. And this makes us excited because now we can use the earth-abundant metals instead of the precious ones. Which brings me to my future work, which is almost intuitive because now we want to understand the mechanisms behind the synthesis of basically combining copper selenide with other materials to find a proper composite material and enhance the performance of their plasmonic properties. Thank you.
Great job. Thank you so much. We've got 3 minutes for questions.
I have a question about the measurement of your plasmonic energy. So I assume you measure these in a solution where there are a bunch of nanoparticles together. I was wondering if you would expect to see any difference if you're ever able to isolate, a single or very few nanoparticles, get them out of solution, drop cast them on a surface, what you would expect to happen to plasmonic resonance.
So that's actually a really good question because so like I said, noble metals are actually the more traditional things that they've been studied. And we actually see that if there are more than 1 nanoparticles for noble metals, especially, there's actually a coupling between the plasmons of 2 adjacent ones, and that actually enhances their plasmonic properties. So what I believe is, and I don't think, to my knowledge, that we have been able to isolate less number of nanoparticles, but I think it actually having more than 1 in solution makes them enhance the plasmonic properties. I hope that answers the question.
Yes, thank you.
Very interesting.
So,
okay, Susan.
No, you go ahead, Feng.
Oh, sure. So interesting talk. I was just curious. You mentioned in your future work, you list out a couple of other kind of ions. Do you have an kind of idea, like what do you think is going to work the best, so that like what are you looking for in terms of the properties to enhance the performance here?
Yes, so actually, thank you for that question. I'm actually really excited about that because what we have here is we were actually trying to look at the different interfaces that we can actually make. So copper selenide is a semiconductor nanoparticle, and if we can actually create a semiconductor metal interface or a semiconductor interface, there are different applications that we can actually use them to. So for example, if we use platinum, platinum is a catalytically active metal. So we can actually use the plasmon to drive a reaction on the platinum surface. So that is something that gets me excited when I think about the interface and how we can leverage the different properties that arise from it.
Yeah, my question was right here too on these composition maps. Should I want the 2 or 3 materials to be well distributed throughout, like the bottom right, or do I want to maximize interface like between purple and green?
That's actually really a good question because I think it depends on what we are looking for. For example, if we have So if you look at the, so the second map, that's the silver copper selenide nanoparticle, and copper silver selenide is actually a well-known thermoelectric material. So that is one property that we can leverage out of it. Whereas if we have a more distinct interface as we have for platinum and gold, those are different properties that we have. So basically we want to understand how we can dictate the mechanism or how we can actually control the morphology. So do we get a distinct interface versus do we get like a completely mixed heterogeneous morphology? That's our entire focus for the next project.
Great, thanks, Riti.
Thank you.
Thank you, very nice. We are on our grand finale poster. Tajal. Awesome, thank you. If you're ready. Uh-oh, you might be muted.
Can you hear me now?
Yes, there we go.
Okay.
Go ahead.
I'm Tejas Sawant. I'm from Department of Chemical and Petroleum Engineering at University of Pittsburgh. And my topic for today is flow-based micro-electrochemical methods for characterizing redox flow battery kinetics. Let's look into the motivation. So energy demand worldwide is continuously increasing, and there is a need to incorporate more and more renewable energy resources into the current energy grid. However, the challenge with incorporating renewable energy resources is that they are spatially and temporally intermittent, which means that the peak energy supply does not coincide well with the peak energy demand. Thus, we need to think about storage of energy when we think about incorporation of renewables. Redox flow battery is a promising technique to use and store renewable energy on a continuous basis. However, for large-scale commercial adoption of redox flow batteries, it's important to understand electron transfer kinetics in these systems. So, to illustrate, I'm showing you here a plot of potential versus current density, which is a typical charge-discharge plot for a redox flow battery. And as you can see, that the discharge curve has primary contributions from the electron transfer kinetics. This is also represented in this plot, where as you go from the blue to the green curve, which is slowing down in kinetics, you see that you require a larger and larger potential to drive the same reaction. This influences the efficiency of the system. So if you think about the voltage efficiency, you want to be as high in voltage efficiency as possible, and you also want to be higher in power density when you think about a practical system. This means that you need to completely start eliminating the kinetic limitations in these systems. Our lab is trying to develop characterization tools to measure electron transfer kinetics of these systems. Why is there a need to develop improved measurements? Because if you look at redox flow battery literature, then the complete literature can be divided into 3 subcategories. The first one is a materials discovery phase, followed by applied electroanalysis, and finally device design. In materials discovery, you generally try to develop novel materials, and then you actually go ahead and apply it into device to see the performance of these novel materials. However, a lack of effort in applied electroanalysis phase makes it difficult to do directed design of RFPs. So our lab is working on this applied electroanalysis phase. Whatever work is done in the applied electroanalysis phase so far has been done with a system called as a rotating disk electrode system. But when we employed this system at high concentrations, which are practically relevant concentrations of electrolytes, then we saw that the expected and observed kinetics were at least a factor of 6 different. Thus, we developed a novel flow cell platform which more closely resembles the operation of a redox flow battery. And it also gives us the kinetics which are more closer to the true kinetics of the system. And now that we have this flow cell platform, we want to incorporate it into a functional flow battery in the future so that we can measure the kinetics of these systems in situ. This will give us the true kinetics of the system while the battery is in operation, and this can also be used to further do directed design of RFPs. Thank you.
Thank you. We are open for questions for the next 3 minutes.
I was going to let the non-chemi people go first. but I'll go ahead while you're thinking of your question. So I have all sorts of questions about redox flow batteries. When I first learned about them, I remember the idea was that they would be like big and stationary and made out of cheap materials.
Mm-hmm.
And when I think about your flow through situation here, it's pretty small.
Mm-hmm.
So talk to me about scaling, like how relevant is your, from what you know about fluid dynamics and so on and so forth from chemical engineering,
Mm-hmm.
how relevant is this little model system to the big thing that I'm envisioning in my head?
Yeah, that's a great question. So this is exactly like what we are trying to do in our lab. So if you think about like the literature, most of the work gets done in like materials discovery phase, where you start developing, like tune the molecules to like make new materials for flow battery applications. And then usually people just employ them on like lab scale model devices and find the performance. So what we are doing is actually develop this applied electroanalysis phase so that we can actually bridge the gap between like lab scale conditions and practical flow battery conditions. So when you think about like this being really tiny, it definitely is tiny. But so for example, we are operating in like the transport conditions, which are more similar to like flow battery operations. So they are still like laminar conditions, which we do want in practical flow batteries. Also, if you think about like the electrodes, these are like micro-electrodes, which are not really representative of what is used in flow batteries. But when you think about real flow batteries, those are like porous carbon electrodes. And when you think about like each particular pore, it can be actually simulated to have the same transport conditions as if it were like a micro-electrode. So we are trying to bridge that gap as much as possible. But yeah, I mean, definitely it's still like far away from like the big batteries that you think of.
Thanks, Tejal.
Mm-hmm.
Anyone else want to squeeze in a quick question? Okay, great job. Thank you to our judges, Aaron Sheridan, Susan Fullerton, and Feng Xiang for your time. And thank you to all the presenters for this speed run. We have another session at 4:15. You can check out the gallery if there's anyone who you missed in the other sessions, and I think the recordings will be coming out soon too. This room is going to stay open because this is where the next session will be. You guys can stay here and chat. I'm going to get up and meander, and I'll be back at 4:15.
Great. Thanks, everyone.